Okay, let's see. Welcome to my stream. Let's get dive right into it. There we go. So yesterday what we did was we looked at, or we did chapter 14. Get status. Get lock. Here we go. We have disassembling chunks, we have constants, and we have line information. So if we cargo run now, and already we get a spammer. That's great. Let me just fix this real quick. There we go. And done. Okay, apologies. So we can cargo run now, and we can see we have the chunk offset in the first column. We have a line number in the second column, and we have special code to not repeat the line number, just put a vertical bar if the line number is the same. Then we have the opcode name. And for constant, we have which constant it is and the value of the constant. So that's all working. And then just at the end of the stream yesterday, let me go back here. I just learned that there's a test suite for locks, and it's right over here. And we were gonna try it out. I just didn't have Dart configured correctly. I think I have it now. Yeah, now it's set up right. I had permissions set wrong. I installed it with my admin login, and I didn't have it working for Joe user, which is me. So if we have a test, maybe what we can do is, and there was a description on how to run this. We could see how bad is my JLOCKS interpretation, and then we can just have it continue for CLOCKS and have that working. And there's this Dart script here. So let me clone this. Let's start off by doing that. We'll clone this repo. Let's use SSH into here. Whoops, I didn't mean to do that. ... My hand was shifted over by one. Okay, git clone. And I think I have it like this. Nope. Maybe I have it like this. There we go. That's a big repo. Okay. So if I go to crafting interpreters, I should be able to just run the Dart thing, just using this command here. So if I say dart tool bin test dart, right, and it's JLOCs, what we should do is, oh, I did compile release last time, didn't I? So locks, interpreter. I'm just following this line here. My code boblocks, blah blah blah. Interpreter is in locks AST, target, release, locks AST. Now let's see how bad it is. Error not found. Ooh, oh, right. What do you have to do? There's a Dart pub get, maybe? I don't use Dart too often, so I thought it was under test. Oh, tool bin. Yeah, pub spec, right? I think it's Dart pub get or Dart get pub. Oh no, there it is. It's working. Yeah. Okay. All right. So let's let that install. Oh, got the dependencies. Good. I thought it would take longer, but no. Okay. There's my Dart command. Ooh, that's not good. 102 tests passed, but 137 tests failed. All right, and then we can use this as our CLOCs. I wonder what are we failing? Expected runtime error. Expected 2 arguments got 1 and got none. Expected return code 70 and got 0. Standard error. Line 5 at expected 2 arguments but got 1. Okay, so I do see it was expecting this, and I did print this out. Expected 2 arguments but got 1. I mean, it's the same. I wonder what the issue is. Oh, and this is just because I printed. Okay, I'm just looking at this next one here. It's expecting it to say foo instance, and I wrote it such that it says instance of class foo. Right. So there's a bunch that we can just fix just by fixing this guy. And I have illegal expression to say if operands must be numbers, but this is saying expected runtime error and got none. So I guess I'd have to take a look at what the actual JLOCs outputs in order to compare my output with missing expected output true on line 5. Oh, am I missing equality for Booleans? Oh, apparently you're supposed to be able to compare classes. Bound methods have identity equality. Interesting. So this is missing from JLOCs. Okay, so we have work to do, but we're not going to do that today. We're going to, maybe that'll be a stream for another time, cleaning up that, all that stuff. How did I end up with 2 windows like this? I don't want 2 windows like this. Okay, so we're on to the next chapter. Let's dig into this. We can actually probably it would be nice if there were a way to say, test chapter 1, test chapter 2, test chapter, or actually 14, right? We're on chapter 14 now. Locks bytecode. We just finished 14, so testing that would be nice and getting that all working. But let's dive right into the virtual machine and see where we go, and then we can always run the Dart thing on CLOCs and see how much fails. Because everything should fail until we're done, right? Although this is, I'm just looking at this error output. It's an unexpected output on standard error. Expected return code 65 and got 0. Missing expected error at A, already variable name in the scope, and I have that. Oh, it doesn't say error at A, already a variable with a name in the scope. And this is on standard error, and maybe it's expecting it on standard out. All right, I'm not going to worry about it. All right, let's dig into the virtual machine here. We've spent a lot of time talking about how to represent a a program as a sequence of bytecode instructions, but it feels like learning biology using only stuffed dead animals. We know what instructions are in theory, but we've never seen them in action. So it's really hard to understand what they do. It would be hard to write a compiler that outputs bytecode when we don't have a good understanding of how that bytecode behaves. So before we go and build the front end of our new interpreter, we will begin with the back end, a virtual machine that executes instructions. It breathes life into the bytecode. Watching the instructions prance around, it gives us a clearer picture of how a compiler might translate the user's source code into a series of them. User source code into a series of instructions. Okay. A virtual machine is one part of our interpreter's internal architecture. You hand it a chunk of code, literally a chunk, and it runs it. The code and data structures for the VM reside inside a new module. All right, so we'll create a new module. Oops, it needs a rust. And then this just contains a chunk. I mean, that's not much, right? Struct VM chunk, which has a chunk. Should it be a reference to a chunk? Or should we hand it, just give it the chunk and move it into here? Use create chunk star. And then in main, mod VM. Oh, these two should be together, right? Oh, and I forgot to finish writing that code. Okay. All right. So 2 warnings that we're not, and that's because we're not using VM anywhere. So we have init and free. Right now they don't do anything. As usual, we'll start simple. The VM will gradually acquire a whole pile of state it needs to keep track of. So we define a struct now to stuff that all in. Currently, all we store is the chunk that it executes. Like we do with most of the data structures we create, we also define functions to create and tear down a VM. Here's the implementation. So we can create a chunk. So this should be an option chunk then. Although technically we should not be able to create. How do we pass the chunk? Oh, we say interpret a chunk. So we're just passing in the chunk. I'm trying to think about, the Rust way to do this would be to create a VM with a chunk, but it sounds like we can create a VM and then pass it a number of different chunks. And this is just going to be a pointer to the currently executing chunk. And it could be null. So init doesn't even initialize the field. And this is a global. That's interesting. So we just have one VM. So we're gonna change that for Rust, as we'll be able to create multiple VMs, right? By just having it this way. Init VM doesn't do anything, and free VM doesn't do anything. But we can create a new VM out of the ether, right? Just impl VM pub fun new self chunk none. And the only issue with making this an option is then we have to unwrap it every single time we do anything with it. Right? Because by statically allocating it here, it's just going to be empty. So we have functions to create and tear down the VM. Calling those functions implementations is a stretch. We don't have any interesting state to initialize or free yet, so the functions are empty. Trust me, we'll get there. The choice to have a static VM instance is a concession for the book, but not necessarily a sound engineering choice for a real language implementation. If you're building a VM that's designed to be embedded in other host applications, it gives the host more flexibility if you do explicitly take a VM pointer and pass it around. That way, the host app can control when and where memory for the VM is allocated, run multiple VMs in parallel, etc. What I'm doing here is a global variable, right? So that was the thing. So I think what we'll do is we will do it this way, and then possibly not even have chunk in here. If we have pub fun, I'm not going to write it now, but if we have a pub fun interpret mut self and chunk, maybe like this. And it's possible that we can just interpret the chunk without even needing to save it inside the struct. So I'll create a new because we're gonna add fields to this, but right now I'm just gonna do this and then see how far that gets us. The slightly more interesting line here is that the declaration of the VM. The module is eventually going to have a slew of functions and would be a chore to pass around a pointer to the VM to all of them. Instead, we declare a single global VM object. We only need one anyway, and it keeps the code in the book a little lighter on the page. All right, well, we're going to be passing it around. Here's init VM, which we don't need. Actually, why don't we do it anyway? We can just say let VM, actually do it in a different order, equals VM new. And that way we actually have it. And then free, just freeze it. We don't actually need that, but I'll write it. Right? Pub fun free, which doesn't, right now, it doesn't do anything. All right. Oh, I forgot to mut self it. Still doesn't like it. Oh, it's mutable. Okay, there we go. And this is probably warning us that we're not actually using VM anywhere. Oh, we're not using chunk yet. Right, we will. Okay, so then free VM. One last ceremonial obligation is the include file. That's fine. The VM is ready and waiting, so let's teach it to do something. All right, so executing instructions. The VM springs into action when we command it to interpret a chunk of bytecode. So we're going to pass in interpret. So right after disassemble, we can just say vm.interpret chunk. And maybe we do want it as pass by reference. Right? Because I think that's the way I wrote it. Okay, and then the VM runs the chunk and then responds with the value from this enum. All right, so we're going to create a interpret result in VM. I guess pub enum interpret result. That's very long, and we're going to have OK and compile error and runtime error. Right? And then so interpret is going to return that, right? VM runs a chunk and responds from the value with a value from here. We aren't using the result yet, but when we have a compiler that reports static errors and a VM that detects runtime errors, the interpreter will use this to know how to set the exit code of the process. We're inching towards some actual implementation. Right. So we'll say pub fun interpret. I'm assuming that we need to be mutable, and then we're going to have the chunk to execute. Yeah, I just wrote that down here. Okay, good. But it's going to return and interpret results. Hi, Epic. How are you? Epic says, yesterday I asked if this register is stack-based VM, but I had to go help someone fix a build environment problem, so I never heard of what you replied. My response is I don't know yet. I haven't looked ahead. I believe that the stack-based version would be a simpler thing to implement than a register-based version. So I'm guessing that's where we're going, but I don't know. I try not to look ahead because I like to be surprised by what's going on. If you want to take a quick peek and then let me know where we're going, that would be fine. So VM chunk is chunk, right? So this is where we assign the chunk to the VM and then we run it here. But we could just pass the chunk down. VM IP is chunk. Oh, I see what they're doing here. They're saying setting the IP to point to the beginning of the chunk of code, right? So this is actually an address. Yeah, it's a uint8t pointer to the beginning of the chunk. So what we're going to do instead is just have an index into the array, and we'll call that our IP. And I think I'm going to try passing this. Epic says, yeah, I totally understand you don't want spoilers. Yeah, but I don't, I don't mind knowing like that kind of a detail. I just don't want to read ahead. Right, so if the IP is going to be an address into the chunk, I'll get rid of that. So this would be self.ip is 0, right? So we're going to just start off at the beginning of the chunk, and then we can say return self-run chunk. Right, and we can just pass the chunk along. And I'm guessing we'll have the IP, and I don't want to store the chunk yet in here unless it's the obviously correct solution to do. But right now I'm just going to pass the chunk along. First we store the chunk being executed, then we call run. Between these two parts is an intriguing line. What is this IP business? Right. Instruction pointer, right? As the VM works its way through the bytecode, it keeps track of where it is, the location of the instruction currently being executed. We don't use a local variable inside run for this because eventually other functions will need to access it. Instead, we store it as a field in the VM. If we were trying to squeeze out every ounce of speed out of our bytecode interpreter, we would store IP in a local variable. It gets modified so often during execution that we want the C compiler to keep it in a register. All right, its type is a byte pointer. We use an actual real C pointer pointing right into the middle of the bytecode array instead of something like an integer index because it's faster to dereference a pointer than look up an element in an array by index. That's true. But I don't want to point, theoretically we could just use an iterator over the bytecode array, but we have to jump around, so we can't really do that. And I'm guessing we have to jump around. The name IP is traditional. Unlike many traditional names in CS, actually makes sense. It's an instruction pointer. PC is, right here. x86, call it IP. 680K, call it program counter. Yeah, IP or PC. We initialize IP by pointing it at the first byte code in the chunk. We haven't executed that instruction yet, so IP points to the instruction about to be executed. This will be true during the entire time the VM is running. IP always points to the next instruction, not the one currently being handled. All right, so here's run. All right, the real fun happens in run. So I'm guessing this is a private function. It's declared static, so it's going to be in C. That means you can't access it from outside vm.c. We'll call it run, and I'm going to say mod.self and chunk, and it's going to return interpret result. This translates to loop. Then we grab the instruction, and if it's a return, then we're done. We also have the other instruction, which is constant. So that's going to have to get handled somewhere, or on the Rust side of things, it's going to have to get handled. So what we have then, we'll do match. I guess we can read byte automatically increments the IP. So I can do that similarly with what instruction is self read byte. Right, and then we can instead of using a macro, we'll just do it this way. We do need to pass in self and chunk. Unfortunately, you got to pass these all over the place. Mod self chunk. And this is going to return a U8. Oh, if we're reading the instruction, we can return the opcode for it. Right, let's take a look at what chunk looks like. Chunk is going to look at this code here. And we should be able to do a read. Because we have write, so we should be able to do read. Let's do that. Hub fun read self. It returns U8 and an index. And just self code of IP. right? So we can then say chunk let value is chunk, or we can just say this, right? Chunk dot read self.ip as it's already as U8, and then we can say into, and then we need to increment IP self IP plus equals 1, and then return down. Will this work? Nope. Oh, we now have IP here. Forgot about that. Read byte doesn't exist. It takes one argument, but two were supplied. Oh, that's dumb. That was dumb. Okay. And it doesn't like this. Oh. Okay, there we go. Now we have 5 warnings. All right, so then after we do the read byte, we're going to say match instruction, because we could just say, all right. And then if it's opcode, op return, then we're going to say return interpret result. Okay. If it's opcode constant, okay, we have to handle this. Rust won't let us get away without handling it. Well, let's just do a to-do. Okay. It's interesting. Read byte and then undef read byte. Okay. This is the single most important function in all of CLOCs by far. When the interpreter executes a user's program, it will spend something like 90% of its time inside run. Or at least it will be in a few chapters when it has enough content to be useful. Right now, it's not exactly a wonder of software wizardry. All right, despite that dramatic intro, it's conceptually pretty simple. We have an outer loop that goes and goes. Each turn through that loop, we read and execute a single bytecode instruction. To process an instruction, we first figure out what kind of instruction we're dealing with. The read byte macro reads a byte currently pointed at by IP and then advances the instruction pointer. The first byte of any instruction is the opcode. Given the numeric opcode, we need to get to the right C code that implements that instruction's semantics. This process is called decoding or dispatching the instruction. Note that IP advances as soon as we read the opcode, before we've actually started executing the instruction. So again, the IP points to the next byte of code to be used. We do that process for every single instruction, every single time one is executed. So this is the most performance critical part of the entire virtual machine. Programming language lore is filled with clever techniques to do bytecode dispatch efficiently, going all the way back to the early days of computers. If you want to learn some of these techniques, look up direct threaded code, jump table, and computed goto. Alas, the fastest solutions require either non-standard extensions to C or handwritten assembly code. For CLOCs, we'll keep it simple. Just like our disassembler, we'll have a single giant switch statement with a case for each opcode. The body of each case implements the opcode's behavior. So far, we handle only a single instruction, op return, and the only thing it does is exit the loop entirely. Eventually, that instruction will be used to return from the current LOCS function, but we don't have functions yet, so we'll repurpose it temporarily to end execution. All right, let's go ahead and support our one other instruction. All right, so this is the constant, right? Let's take a look really quickly at our disassembler to see how we disassemble that constant, because this is going to be the same code, right? We're going to say let constant is equal to, oh, and then we're going to have something called read constant, and then print value. How do I print the value? Self constants print value. Chunk. Oh, so we have an interesting thing here. If we're going to read the constant, and that's something we're going to want to do, is dereference right out of the VM. So I should be able to say self chunk read constant. And that gives me the constant. And then I want to print the value of the constant. Now I need the... Should I try to call this print value? Well, this print value takes the index of the constant and prints out whatever that index is. It doesn't... So now I'm thinking I just do this. Which is a little awkward. Because now we're having print code directly in our interpreter instead of calling it like a value constant.print. But value in my book, value is just a type. You can't do an impl on it to do like value.print. Okay, so we'll leave it like this for now until something breaks, and I will add a read constant, or maybe this should be called get constant. Oh no, we can't just do it here, we have to do it here. This one's called read constant and this one's called get constant because we need to be able to increment IP. Read constant, not self chunk. This is why you store the chunk in the VM. And then I have to import value. Use create value star because it returns a value. And what we're going to do is say self chunk read byte. Self chunk. No, not self chunk. Index is equal to chunk dot read self dot IP, and that's a U8 as usize. So that's going to give us our index. We'll say self dot IP plus equals 1, and then we're going to say chunk dot get constant and give it the index, and that'll be what's returned. And down here we're going to say pub fun get constant self, and it returns a value self. Oh no, it gives us the index, usize, and self constants. Let's take one more look at the value. There's a write, there's a free, there's a print of read value self which usize self values which. Okay, so this is a little awkward, but this is going to work. Self constants read value index. And let's see what blows up. Oh, I forgot to return a value. And read constant. Oh, I need to give it the chunk. Okay. That seems to be compiling. Does it run? It printed out 1.2. Right, which is what the const does right now. Right, you get the constant right here and print it out. It also does the disassembly, so I think that's working. Execution tracing. Yeah, so I skipped over this part here. We don't have enough machinery in place yet to do anything useful with the constant. For now, we'll just print it out so we interpreter hackers can see what's going on inside our VM. I call it printf necessitates an include, which is the standard IO. We also have a new macro. Read constant reads the next byte from the bytecode. Right, so that's what I was going through all of this business now. Here we have read constant, which reads the next index, the next value out of the chunk, converts it to a usize, and then we can pass that into get constant to actually return the constant value. So that seems to do the trick. In later chapters, we'll add a few more instructions with operands that refer to constants, so we're setting up this helper macro now. Like the previous read byte, read constant is only used inside run. To make scoping more explicit, the macro definitions themselves are confined within that function. We define them at the beginning, and because we care, undefine them at the end. Undefining these macros explicitly might seem needlessly fastidious, but C tends to punish sloppy users and the C preprocessor doubly so. Alright, for run clocks now, it executes the chunk we hand-authored in the last chapter and spits out 1.2 to your terminal. We can see that it's working, but it's only because our implementation of constant has temporary code to log the value. Once that instruction is doing what it's supposed to do and plumbing that constant along to other operations that want to consume it, the VM will become a black box. That makes our lives as VM implementers harder. To help ourselves out, now is a good time to add some diagnostic logging to the VM, like we did with chunks themselves. In fact, we'll even reuse the same code. We don't want this logging enabled all the time. It's just for us VM hackers, not LOX users. So first we'll create a flag to hide it behind. Oh, I see. Okay, so this is where we go Rust features flags. How do we do features? Because that's the equivalent of doing a feature. And then we could just say config feature is webp. Okay, so we can do that here, right? We can say in our main loop, disassemble instruction. So what does disassemble instruction look like? We'll have to make it public. And we need to pass in just the offset. That's all we care about is the offset, right? We don't need to do this weird pointer arithmetic casting to an int. We have the index. So we can say config feature equals, what was the feature name? Debug trace execution. And do we do snake case for it? Or do we use okay, kebab case, I guess. Debug trace execution. Let's do it like that, and then we'll call self.chunk.disassemble instruction self.ip. Right. So if this feature is enabled, then we'll get that. And if not, what's the complaint? Oh yeah, we're not using those two yet. Okay. So now in our cargo.toml, we have to add that as a thing, right? Features. How do we do it? We just say debug trace execution. Is that all we need to do? And then we can either cargo run, right? And then we can say cargo run features. Where does it say? How do you add the feature onto the Pensy features? So just features. Debug trace execution. Aha. Okay, so right, it's not self chunk, but it did work, right? Because it built here and it ran here, and now it actually tried to compile the code. Disassemble. It's not self. It's just on its own. Ooh. Len is 1, but the index is 1. So that didn't work. We tried to get the wrong constant. Interesting. If I pass in offset of 0, oh, so which line did it die on? Line 23. Oh, line 23 of value, right. Because we passed in 1 for our index instead of 0 for our constant index. For some reason it read a 1 here, and I don't know why. And it was on the wrong line. Oh, I know why. Because I incremented the read byte before I had a chance to disassemble the instruction. This has to happen first. Okay. Before I do this. That's the problem. Okay, let's try this now. There we go. So this is our disassemble, right? And then this is our execution. We printed it out and returned, and we're done. All right, so we have both of those now. We can actually turn that on or off using the feature flag. So that's section 5.1, right? Disassemble instruction takes an integer byte offset. We store the current instruction reference as a direct pointer. We first do a little pointer math to convert IP back to a relative offset, right? So we don't have to do that in our code because we already have the offset instead of the direct pointer. Then we disassemble the instruction that begins at that byte. As ever, we need to bring in the declaration of the function before we can call it. I know this code isn't super impressive so far. It's literally a switch statement wrapped in a for loop, but believe it or not, this is one of the two major components of our VM. With this, we can imperatively execute instructions. Its simplicity is a virtue. The less work it does, the faster it can do it. Contrast this with all of the complexity overhead we had in JLOX with the visitor pattern for walking the AST. All right, so let's clippy this. I think we're just going to have to live with these until we're ready to use them, or we can just comment them out. Okay, so git add source, git commit -m, section 15.1, which was called an instruction execution machine. There we go. All right, so 15.2 is a value stack manipulator. Okay, so this might be the answer, right? We might be doing stack-based stuff instead of register-based stuff. In addition to imperative side effects, LOX has expressions that produce, modify, and consume values. Thus, our compiled bytecode needs a way to shuttle values around between different instructions that need them. For example, print 3 minus 2. We obviously need instructions for the constants 3 and 2, the print statement, and the subtraction. But how does the subtraction instruction know that 3 is the minuend and 2 is the subtrahend? How does the print instruction know how to print the result of that? Yes, I did have to look up subtrahend and minuend in a dictionary, but aren't they delightful words? Yeah, I think I remember learning these like in 3rd grade. We had to memorize them all. Addend and augend. And all those multiplicand and multiplier and product and dividend and divisor and quotient. Okay, to put a finer point on it, look at this thing right here. Function echo, print n, return n. Print echo, 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 echo. I wrapped each sub-expression in a call to echo that prints and returns its argument. The side effect means we can see the exact order of operations. I'm going to take a look here and see what this looks like. One, 2, 3, 4, 5, 9, 12. So there's the 9, right? And this is a 3. So you can see 1, 2, 1 and 2 make 3, then 4 and 5 make 9, and then we have the 3 and the 9, which make 12. Okay. Don't worry about the VM for a minute. Think about just the semantics of locks itself. The operands to an arithmetic operator obviously need to be evaluated before we can perform the operation itself. It's pretty hard to add a plus b if you don't know what a and b are. Also, when we implemented expressions in JLOCs, we decided that the left operand must be evaluated before the right. Right, so we did left, right, and this is the left of the bigger expression. This is left, right. And then that's the right of the bigger expression, and then that's the sum. We could have left evaluation order unspecified and let each implementation decide. That leaves the door open for optimizing compilers to reorder arithmetic expressions for efficiency, even in cases where the operands have visible side effects. See in Scheme, leave evaluation order unspecified. Java specifies left to right, like we do for locks. I think nailing down stuff like this is generally better for users. When expressions are not evaluated in the order users intuit, possibly in different orders across different implementations, it can be a burning hellscape of pain to figure out what's going on. Right, so this is what we see. Our old JLOCs interpreter accomplishes this by recursively traversing the AST. It does a post-order traversal. First it recurses down the left operand branch, then the right operand branch, and then finally evaluates the node itself. After evaluating left operand, JLOCs needs to store the results somewhere temporarily while it's busy traversing down through the right operand tree. We use a local variable in Java for that. Our recursive tree walk interpreter creates a unique Java call frame for each node being evaluated, so we could have as many of these local variables as we needed. In CLOCs, our run function is not recursive. The nested expression tree is flattened out into a linear series of instructions. We don't have the luxury of using C local variables, so how and where should we store these temporary values? You can probably guess already, but I want to really drill into this because it's an aspect of programming that we take for granted, but we rarely learn why computers are architected this way. Hint, it's in the name of the section, it's how Java and C manage recursive calls to functions. Let's do a weird exercise. We'll walk through the execution of the above program a step at a time. Alright, so we have the constant 1 and the constant 2. We add them to get 3, and then we don't need these constants anymore. 3 has to hang around until we evaluate the right side of the expression. And then we get to use it after the right side of the expression is complete. On the left are the steps of the code. On the right are the values we're tracking. Each bar represents a number. It starts when the value is first produced, either a constant or the result of an addition. The length of the bar tracks when the previously produced value needs to be kept around, and it ends when that value finally gets consumed by an operation. As you step through, you see the values appear and later get eaten. The longest lived ones are the values produced from the left-hand side of an addition, those that stick around while we work through the right-hand operand expression. In the above diagram, I gave each unique number its own visual column. Let's be a little more parsimonious. Once the number is consumed, we'll allow its column to be reused for another later value. In other words, we will take all of the gaps up there and fill them in, pushing in the numbers from the right. Okay, how does that help? There's some interesting stuff going on here. When we shift everything over, each number still manages to stay in a single column for its entire life. Also, there are no gaps left. In other words, whenever a number appears earlier than another, then it will live at least as long as that second one. The first number to appear is the last number to be consumed. Last in, first out. Why, that's a stack. In the second diagram, each time we introduce a number, we push it onto the stack from the right. When the numbers are consumed, they're always popped off from the rightmost to the left. Since the temporary values we need to track naturally have a stack-like behavior, our VM will use a stack to manage them. When the instruction produces a value, it pushes onto a stack. When you need to consume one or more values, it gets them by popping them off the stack. Maybe this doesn't seem like a revelation, but I love stack-based VMs. When you first see a magic trick, it feels like something actually magical, but then you learn how it works, usually some mechanical gimmick or misdirection, and the sense of wonder evaporates. There were a couple of ideas in computer science where even after I pulled them apart and learned all the ins and outs, some of the initial sparkle remained. Stack-based VMs are one of those. Heaps, the data structure, not the memory management thing, are another, and Von Pratt's top-down operator precedence parsing scheme, which we'll learn about in due time. To take a bit of the Sheenhoff stack-based interpreters aren't a silver bullet. They're often adequate, but modern implementations of JVM and CLR and JavaScript all use sophisticated just-in-time compilation pipelines to generate much faster native code on the fly. Alrighty, it's coding time. Alright, so we're going to have a stack. Good morning, Nudep. Thank you for joining my stream. So we're going to stick this in. We're clean, right? Oh, no, we're not clean. We added that. Oh, I forgot to add this to the amend. How do I do an amend? There we go. It was right in my history. Perfect. All right, we implement stack semantics ourselves on top of a raw C array. So in our world, we're going to just use another vec. We're going to call it stack. Vec, and it's going to be of value. Okay, and then we'll have to initialize it here. All right. The warning is because we're not using it yet. We implement stack semantics ourselves. At the bottom of the stack is the first value pushed, blah, blah, blah. So we're going to use just vex, push, and pop for that. This is talking about how stacks work. What about when the stack is full, you ask, clever reader? The C standard is one step ahead of you. It is allowed and well specified to have an array pointer that points just past the end of array. Yep. But we don't care because we're using vec. I remember it like this: stack top points to where the next value. Okay, I'm not going to worry about. Oh, there's a max, a stack max. Given our VM is a fixed stack size, means it's possible for some sequence of instructions to push too many values and run out of stack space. The classic stack overflow. We could grow the stack dynamically as needed, but for now we'll keep it simple. Since VM uses value, we need to include it in its declaration. And there's reset stack. So reset stack is just setting vec new. Are we going to need this elsewhere? Elsewhen? Maybe not. I don't know. But we can add it. Like that. The stack protocol supports two operations, push and pop. Okay, not going to worry about that because we already have push and pop on the stack. If you're rusty on your C pointer syntax operations, this is a good warm-up. Right, it assigns value to VM stack top and increments stack top. Pop does decrements the stack top and returns what it's pointing to. That all makes sense, although I don't see it checking for stack max. We need a stack max check in there somewhere. Stack tracing. Ooh. We have a working stack, but it's hard to see that it's working. When we start implementing more complex instructions and compiling and running larger pieces of code, we'll end up with a lot of values crammed into that array. It would make our lives as VM hackers easier if we had some visibility into the stack. To that end, whenever we're tracing execution, we'll also show the current contents of the stack before we interpret each instruction. All right, so this is going to go in debug trace execution. And what we're going to do then is, because I don't want to have to put the feature thing on every single line, we're going to just make a block. So we're going to say print bang, and how many spaces is that? 1, 6, 7, and 3 is 10. Okay. And then for value, we're going to print each value. Slot in. Okay, so we're starting from the beginning of the stack and going to the end in self stack. Print bang. Looks like open brace. We're going to print the value which we're going to have to get in a second. like that. Newdip says, I discovered your YouTube channel when doing last year's Advent of Code. You've been an inspiration in consistency and discipline since then. Thank you. Thank you. This is like the one thing I'm consistent in my life here. So I will take that compliment. Thank you. All right. So the slot. Oh, yeah. The slot is the value, right? That contains the value. So we can just do this. Slot. Boom. Right. So it's open space value space close, which is just this. We loop printing at each value in the array starting at the first. This lets us observe the effect of each instruction on the stack. The output is pretty verbose, but it's useful when we're surgically extracting a nasty bug from the bowels of the interpreter. Stack in hand, let's revisit our two instructions. First up is the constant. So instead of just printing it out, we're going to push it. So that's pretty straightforward. And we'll just say self.stack.push constant. In the last chapter, I was hand-wavy about how the op constant instruction loads a constant. Now that we have a stack, you know what it means to actually produce a value. It gets pushed into the stack. And op return is going to, just pop and print. Okay, we can do that and then print out the result. And then return, okay. So we can just say print lin value. Right, and we'll just say self stack that pop on run. Then we make op return pop the stack and print the top value before exiting. When we add support for real functions as clocks, we'll change this code, but for now it gives us a way to get the VM executing simple instruction sequences and displaying the result. Epic says, I started a system update download while on a conference call. So I don't know why the audio got so bad. Yeah, that's the equivalent of like downloading megabytes of YouTube videos that right in the middle of Zoom. Yeah, you just need a bigger bandwidth. That's all. It gives you an excuse to get more bandwidth out of your provider. All right, so this is still giving us a warning. What's the warning? A reset stack isn't called anyway. All right, so I'm gonna blow it away. We don't need it. And if we use it later, we can always add it back. All right, so let's see. Does this run? Or does this die? It is printing out 1.2, but we're not seeing this yet because I didn't run it with the feature. Aha! Move a cursor. Oh, I need to ampersand it. Is there a way to have that feature automatically turned on? Does anybody know? If in Rust you can put in your cargo.toml, enable the feature. I have the feature here. And I'm using it. I just don't have cargo tree. No, that's pretty simple. Okay. But there should be maybe a way to say enable this feature. Build scripts can look at cargo feature. Oh, well, I'll have to look that up because it'd be nice to just be able to do a run. Right, from main, I can just say run, and right now it runs without that feature enabled. But here we go. We can see we're executing this instruction. The stack was empty here. There's nothing. This is a blank line. We executed this instruction, which pushed 1.2 on the stack, and then we returned and we just popped the stack and printed it. So that's section 15.2 done. It was what, a stack-based something. That was a long chapter. A value stack manipulator. Let's see if I can copy paste this. Yep. Perfect. All right, so 15.3. There we go, an arithmetic calculator. Let's get into that. The heart and soul of our VM are in place now. NewDep says, I think you can add default equals. Okay, let's try that. In place of this or in addition to this? And then how do I turn that off if I want to turn it off? In addition to it? Okay, yep, that worked. But now how do I turn it off? If I wanted to run it without that. All right, we're going to leave it like this for now. Default is a special key in features, Epic says. Okay. Well, this seems to do the trick. So thank you. Appreciate it. And that way we can run it inside Vim. All right. So the bytecode loop dispatches and executes instructions. The stack grows and shrinks as values flow through it. The two halves work, but it's hard to get a feel for how cleverly they interact with only two rudimentary instructions we have so far. So let's teach our interpreter to do arithmetic. We'll start with the simplest arithmetic operation, unary negation. All right. Okay, yeah, this is going to get annoying if we keep doing these in alphabetical order, because it means my translator here has to update every time we add something. So I'm going to stop doing it alphabetically, and I'm just going to stick him at the end. Negate. And we'll just have to live with the discrepancy between the two VMs. Op negate. And that's now that adding that thing is going to bubble up everywhere, right? Every place that we use it. So we execute it like so. So in VM, opcode op negate is just push negative pop. So we can say let value equals self read constant chunk. Actually, we can just negate, right? Oh no, we need to pop it. Sorry. Self stack pop. And then self stack push negative value. Right? In debug, we're going to have to add this. Oops. Opcode negate. I guess I could get rid of the second op here. Self, and it's a simple instruction. Op negate offset. That's good. And then we can try it out in our test chunk. And that's in main. And that's right here, right? Chunk, right? Opcode, op negate. 1, 2, 3. All right, let's see what I blew up. Doesn't like this. I cannot apply unary operator to an option F64. That's true. Okay, that works. Run. Haha, look at that. So op constant pushed 1.2, op negate pushed negative, popped that and pushed negative 1.2, and op return printed the negative 1.2. Wow. Magical. NewDep says no default features. Let's try that. Cargo run, no default. Perfect. Thank you very much, NewDep. Okay, so unary operators aren't that impressive. We still only ever have a single value on the stack. To really see some depth, we need binary operators. LOX has 4 binary arithmetic operators. We'll go ahead and implement them all at the same time. Yeah, Epic says, VM calculator success. We got a 1-op calculator. All right, let's add these other 4 ops and see how well that goes. This is going to be interesting because now we have fancy little... Okay, so we'll write a function just like we did for the other macros. First, we're going to add to our chunk. We'll add these 4 operators. Op add, op subtract, op multiply, and op divide. Right? And then we'll add constants for those. 4, 5, and 6. Subtract. Multiply. Got to get it in the same exact order. Otherwise it's not going to work. So that's that bit. Now in VM, we got to add those 4 instructions. Op code, op add. And it's going to be this binary op. Oh, yeah, okay. So that's going to be interesting. How do we handle this? Oh, we can use standard ops, right? Can I pass in... Can I pass in the function type? I want to basically I want to say something like they have here. We have double B pop, double A pop, and then A op B, and they have this while false business just to put it in braces to make the macro easier. So that's a C preprocessor thing that I'm not going to worry about in the Rust code. The idea here would be to say let B equals self stack pop. Ah, come on, pop, unwrap, and let A be self-stack pop unwrap, and then we want to say, self-stack push A plus B, right? We can just do that, and do that for each instruction. But it would be nice if we had a little binary op thing where I could just say, op code op subtract, and which results in self binary op standard ops sub. I can't do that, right? I would need to be able to pass in some sub function. How do you declare a function, right? You say fn like this. A value. I don't know how to declare the syntax. Oh, it would be in binary op, right? So fun binary op what self and function a value b value returning value, right? And then we'd say basically these lines here, except instead of push A plus B, it would be push, and this probably needs a name, right? Op AB. Can I do this? And then just make a function add, which is A value, B value, and returns a value, and returns A plus B. Will this even work? Let's see. Oh, no, subtract. don't want it like. Expected one of. Oh, op colon. Yes, right? Oh, and you can't give it arguments this way. How do you declare a function? Rust pass function as argument. There you go. Oh yeah, I could just pass in the. I remember doing this for Advent of Code, so but I don't do it often enough to remember the syntax. So we should be able to just pass in this. Right, I should be able to just pass in something that says, oops. A, B, A minus B. I should just be able to do that. A slow being says, why are you learning Rust? It keeps my mind active, and I enjoy, actually, after I played with Rust a little bit, I really enjoy it a lot. So I just want to keep going and see if I can get better at it. And obviously I need to get better because this is terrible. Oh, it's not capital FN, it's lowercase FN. Match instruction now. Oh, op multiply and op divide are not covered. But what else? I mean, did this actually work? Did this actually work? If I say multiply and divide, oh, up here in instruction. Okay. Rust streaming generally does attract the best viewers, doesn't it? If you're gonna behave like that, a slow being, then I think we can agree that maybe this is not the best stream for you. Okay, so where are we? Right. So we did this, and now we have to deal with the disassembly, which I'm scanning forward to because I want to get this thing to compile. Okay, here we go. So it is just simple instruction. Add, subtract, multiply, and divide. And then we can just change op negate, op add, op subtract. It's hard to type in all caps. Multiply. 5. There we go. All right. Whoa! So this business actually worked. Well, I don't know if it worked. Let's test it, right? But self binary op AB A plus B. That's wild. Okay, so let's scroll back. Right. So we did this part. We did the bytecode business here. The only difference between these four instructions is which underlying C operator you ultimately use. So avoid repeating code 4 times, I wrapped it in a macro. So this is I'm kind of getting away with this as our macro, just like I did with the read constant and read byte. I have a separate function to do that, and this seems like it might actually do the trick. I admit this is fairly adventurous use of the C preprocessor. It's not that bad. I hesitated to do this, but you'll be glad in later chapters when we need to add type checking for each operand and stuff. It would be a chore to walk you through the same code 4 times. Did you even know that you can pass an operator as an argument to a macro? Now you do. The preprocessor doesn't care that operators aren't first class in C. As far as it's concerned, it's all just text tokens. I can feel the temptation. Not only do I feel the temptation, but I have abused this mightily in my career. The outer do-while loop probably looks really weird, yeah, because you're saying do-while false, but the way C works is this will execute once and then hit the false and then stop. And the reason to do it is just to make the syntax nicer with the semicolon there at the end. Right, so they're explaining why here in C you don't want to do that without the do while. It's because this little wacky semicolon at the end of wake up, now there's two semicolons, and that gets annoying. And if you do it this way, then you break this up. So I'm not going to go into the issues with C. Where were we? Right, so the body that macro does is straightforward. A binary operator takes two operands, so it pops twice. It performs the operation on those two values and then pushes the result. Right? Note that we assigned the first popped operand to B, not A. It looks backwards, but that's because of the way stacks work, right? You pop the second value first and then the first value second. And we undef binary op. We don't need to do that. Here's the disassembler part. So let's actually use it. Here we go. So let's go to main. So I think, yeah, so we have this part here. We write the constant. So the negate is down here. Okay, I see. So we can just put everything in between here. So that constant, we'll use shadowing. Chunk, add constant, 3.4. Chunk, write, opcode, op constant, 1, 2, 3. So that's the line number, 1, 2, 3. Chunk, write, constant, 1, 2, 3. Everything's going to be on 1, 2, 3, and then chunk, write, opcode, op add, 1, 2, 3. I don't understand where the lambda's A and B coming from. Oh, that's a good question. So what this is passing in a function here, right, as this op function. And it just takes these two values. So that when I call op, it says, okay, I'm using this op. This is the function here, A and B, which is these two A and B's down here. And it just returns this value. This is a function, right, which returns a value. And this is a function which takes these two arguments, which are these two arguments, and returning this value here. So AB, so it compiles. We haven't tested it yet. I may have gotten this completely wrong, but this is the way I'm reading it is that this op goes to this op. This passes the A and B into this function, which ends up being this A and B, which does this calculation, which results in a value return, and then it pushes it onto the stack. So let's see if that works. So we have op add, and then we'll do it again for divide. We don't want to do it after the add, and it's going to be 5.6, right? And then we'll do a divide, followed by a negate, right? That looks all correct. The addition goes first. The instruction for the left constant 1.2 is already there, so we add 3, 4. Then we add those two using op add, leaving it on the stack. That covers the left side of the division. Next we push the 5, 6, divide the result of the addition by it. Then we negate the result of that. Note how the output of op add implicitly flows into being the operand of op divide without either instruction being directly coupled to each other. That's the magic of the stack. It lets us freely compose instructions without them needing any complexity or awareness of the data flow. Stack acts like a shared workspace that they all read from and write to. All right, let's see if it works. I have no idea if it worked. So op constant, so we have an empty stack here. We push the 1, 2. We push the 3, 4, so now we have 1, 2, and 3, 4. We add them, 4.6. And we push a 5.6, so we have 4.6 and 5.6, and then we divide the two. And I'm assuming that's the division. What's 4.6 divided by 5.6? 82148571. Yep, so that worked. And then we negate that value, and then we return, and that gets printed. So I think it's all working. Aren't they redeclared in binary op? So this, I could call this Q and R. Right, they don't have to have the same variable text, right? So if I do that, now you can see the add still works, right? The names are not the important thing. It's the fact that there's two parameters. Oh, where is it? Down here. There's two parameters, A and B. Right? So these could be Y and Z, right? Or whatever. And all we're doing is we're saying this is a function, a nameless function that takes two arguments and returns the sum of those two arguments. And this is saying this is a function which takes arguments A and B and returns a value. And it could be n-ary. Nudep says, oh, I see the lambda is the variable up. Yes. Yeah, I'm sorry. Maybe I didn't understand your question correctly. But this text that I highlighted turns into op, which is our function that we call. Let's put those back just to be consistent. But that's neat. I like the way Rust lets me do that. That's not something you can easily do in C. You'd have to use pointers to functions. And then each one would be unique. All right, you may as well get it out of your system now. This is the last chunk we'll build by hand. When we next revisit bytecode, we'll be writing a compiler to generate it for us. Okay, so that means, let's do a check, let's do a Clippy. And what was the name of this section? An arithmetic calculator. So let us copy that. And, ooh, all variants have the same prefix op. Yeah, okay, let's clean that up. Why not? And now I'm going to have to fix every place it exists. Op something. Not op code. Oops. That's opcode, and we have all these, 2x. That's okay, and then all the other ones are going to be broken as well. So let's fix those. Come on. I'm trying to hit 2 and I hit W. What else? Oh, right. There we go. Okay, so Clippy should be happy with that. Git commit -m section 15.3 an arithmetic calculator. Okay, a git push. So we finished chapter 15. Wow, that went faster than I thought it would. Where is my? Here it is. Very good. Okay, so I guess we have two options. It's right now for me it's 8:30 and I like to end at around 9. So we can either continue or we can call it a stream. Let me take a quick peek at the register-based bytecode. For the remainder of this book, we'll meticulously implement and interpret around a stack-based bytecode instruction set. There's another family of bytecode architectures out there, register-based. Despite the name, these bytecode instructions aren't quite as difficult to work with as the registers in an actual chip like the x64. With real hardware registers, you usually have only a handful for the entire program, so you spend a lot of effort trying to use them efficiently and shuttling stuff in and out of them. Register-based bytecode is a little closer to the register window supported by SPARC chips. In a register-based VM, you still have a stack. Temporary values still get pushed onto it and popped when no longer needed. Epic says, register-based for the win, yeah. Take a look at this little lock script. var a equals 1, var b equals 2, var c equals a plus b. In our stack-based VM, the last statement would get compiled to something like load a, load b, add, store c. Don't worry if you don't fully understand load and store instructions yet. We'll go over them in much greater detail when we implement variables. When we have four separate instructions. That means 4 times through the bytecode interpret loop. 4 instructions to decode to dispatch. It's at least 7 bytes of code. 4 for the opcodes and another 3 for the operands, identifying which locals to load and store. 3 pushes and 3 pops. A lot of work. In a register-based instruction set, instructions can read from and store directly into local variables. The bytecode for the last statement above looks like add ABC. The add instruction is bigger and has 3 instruction operands that define where in the stack it reads the inputs and writes the result to, but since local variables live on the stack, you can read directly from A and B and then store the result right into C. There's only a single instruction to decode and dispatch, and the whole thing fits in 4 bytes. Decoding is more complex because of the additional operands, but it's still a net win. There's no pushing and popping or other stack manipulation. The main implementation of Lua used to be stack-based. For Lua 5.0, the implementers switched to a register instruction set and noted a speed improvement. The Lua dev team wrote a fantastic paper on this, one of my all-time favorite computer science papers, the implementation of Lua 5.0, which I'm not going to read on stream. Oh, it's a pretty short paper, but that I will read off stream. I will put it in chat in case somebody else wants to take a look. Okay. The amount of improvement naturally depends heavily on the details of the language semantics, specific instruction set, and compiler sophistication, but that should get your attention. That raises the obvious question why I'm going to spend the rest of the book doing a stack-based bytecode. Register VMs are neat, but they are quite a bit harder to write a compiler for. Yeah, that's what I was saying at the beginning. Epic, when you asked me whether this is register-based or stack-based. The stack-based is so much easier. For what is likely to be your very first compiler, I wanted to stick with an instruction set that's easy to generate and easy to execute. Stack-based bytecode is marvelously simple. It's also much better known in the literature and the community. Even though you may eventually move to something more advanced, it's good common ground to share with the rest of your language hacker peers. Next chapter, scanning on demand. So, yeah, I think what I'm going to do is I'm going to do this chapter tomorrow. A scanner, compiler, and virtual machine. So we're going to have to rewrite the scanner, right? That we wrote for the AST version of LOX. Scanner is going to generate tokens. Tokens are going to go to a compiler. A compiler is going to generate, instead of an AST, it's going to generate bytecode chunks. And then the VM is going to get the chunk to run. I did sneak in a few interesting differences compared to JLOX Scanner. Okay, so we will work on Scanner tomorrow. One of the things I can finish out with is the thing I started the stream with our Dart check. Let's take a look at what all these errors are. I see a bunch of, let's start with the first failure. Unexpected output on standard error. Line 6 at underscore expected. Expected return code 0 and got 65. Missing expected output A on line 14. So let's take a look at what this test is. Expected A. And if I run this, we see line 6, expect underscore, expect open print after function name. Oh, okay, there's bug number 1 in our locks, JLocks, is that it's not accepting underscore as a valid identifier character for function names. All right, well, let's fix that. I don't need this window, right? I can just go over here and we can have a pair of windows. Right, let's open up a new one here. Maybe make it 100 wide. to support Rust format, and then we can go in here. Documents, dev, locks AST, and the bug is, we're in crafting interpreters. Let me just copy this command here. Dev, crafting, and let's take a look. Oh, I already have the less. Okay. All right, so let's see if we can fix this one at least. Let me go to the end. There's 102 tests passed, 137 tests failed. Let us see if I can figure out, is it in the scanner where we check? Okay, I do allow underscores there, right? If it's ASCII alphabetic or it's an underscore, then scan the identifier. Oh. Scanner is alphanumeric. Where does this get used? Alphanumeric is just checking to see if is ASCII alphanumeric, I should say, or CH equals underscore. I think that's the bug, is that we're just checking to see if it's alphanumeric and not underscore. And we can actually fix them in our scanner up here. Is alphanumeric. We should just be able to call that same function. All right, I got lost already. So we can say is scanner is alphanumeric C. Oh, if. Will this compile? Nope. Oh, I forgot the arrow. Expected enum option found char. Oh, okay. I mean, I could just make it a sum. Okay. Cargo. Build. Release. Because I'm using the release version of it. Here. Built. Ooh, look at that. We passed 22 tests now. 108 tests passed, 131 tests failed. So a few more tests passed because of that one bug. That's good. Can we fix one more? Unexpected output on standard error. And that's this test here. Use this as var. Expect variable name. Missing expected error. Error at this expect variable name. Huh. Newdep says, not sure if it matters, but alphabetic is different than alphanumeric. So I'm using alphanumeric. Oh, we don't want it to start with, you're right, we don't want it to start with the number. You're absolutely right. So right. So I should check alphabetic or underscore here still. That should still be the case. C is alphabetic or C equals underscore. Yeah. All right, let's just rebuild that and just double check that that didn't break anything. Yeah, okay. We're still at 108, 131. Very good. Yeah, thank you, Newdep, for pointing that out. Appreciate it. All right, so that's that bug fixed. Git status, git add source, git commit, allow underscore characters in identifier names. Okay. So this is saying we have a this. Var this equals value. So it's expecting 2 error at this expect variable name. And what do I have? I have line 2 at this expect variable name. So, okay, so that's just my error reporting being slightly wrong, right? What am I doing here? So with the runtime error, it just reports it here. Runtime error. Should this just be error at? Like that? And up here as well? Is that the issue? Let's try. No. It says unexpected output on standard error. Line 2, error at this expect variable name. Oh, I forgot the colon. Hopefully that's the only issue, is that text isn't exactly right. Oh, no, it's still complaining. Maybe this needs to be in the brackets. Error at this expect variable name. I didn't typo it, so that looks okay. I can put the line in brackets. Oops. Maybe like that. Okay, that was it. So now we got to 25. Expected runtime error variable, undefined variable not defined. Expected return code 70. Oh, right. Yeah, so we don't have all those fancy schmancy return codes. I guess a runtime error should result in a 70. How are we doing this in source main? How are we returning errors? We returned 65 for any error return, although this one got a 0. This is returning okay if it gets here. So maybe we should say not parser success. Oh no, this is returning a LOX result if it fails. This is returning a runtime error if that fails. This, I guess, is not returning a runtime error, right? If we look at the interpret code, it just returns a Boolean of whether it succeeded or not. And that's because we're throwing away the error here. So maybe we need to just return a result. And then just execute it with a question mark. And get rid of that success. It certainly simplifies the code a bit. What are we doing? Oh, okay. We have 2 warnings. Oh, because we need to, oh shoot. I forgot not to run it in here. Oh, we gotta kill it now. Huh? Why can't I kill that? Here we go. Now it's killed. Yeah, don't run it in the air because you can't kill it. All right. Right. So we need to handle this now. This needs to be question marked, and that way it'll return the LOX result. But it'll still do 65 instead of 70. So, but let's see if we at least get that. Yeah, and got 65. All right. So we need to be able to switch on the type of error we get out of here. instead of saying if self-run buff is error, we can just say match self-run buff. And we can say if it's okay, standard process exit 0. If it's error locks results runtime error, does runtime error have data in it? It does. With whatever, then standard process exit 70. And then I'm going to just say for everything else, just do 65, and then we can figure out what they're expecting based on the test suite. Right, and this goes away because we never exit out of that match, right? Okay, let's build that and see if we're getting closer. Expected runtime error, undefined variable not defined. I got none. Okay, let's run this. Oops. Thought I had that. Cargo, run, crafting interpreters, that. Line 1, error not defined, undefined variable not defined. Expected runtime error, undefined variable not defined. I got none. Got none. That's interesting because I'm definitely outputting that. How did we get no error? Let's take a look at the test itself. Print not defined. Expect runtime error, undefined variable not defined. I'm just looking to see if I typoed this, but I don't think I did. No. Let's take a quick look at the test itself and see what, maybe it's expecting something. Expect runtime error. So it looks like it's parsing the file itself and looking for / expect runtime error something. All right, so that's good. We can take a look where's this pattern used. First match line. We expect the runtime error exit with EX software. I wonder if it did. Yeah, it did. So it exited with the correct code. Runtime error line is line num. Expected runtime error is match 1. I guess match 0 must be the whole expression and match 1 must be the sub-expression here. Okay. Expectations plus. Expected errors is not empty and expected runtime error is not null. Oh, that's it. That's an error checking thing. Okay. Then what do we do with this expected errors? Expected runtime error. Validate runtime error. Okay, so this is what we're seeing, right? Expected runtime error something and got none. Right? Expected runtime error something and got none. So we're seeing exactly this. Oh, if error lines.length is less than 2. Huh. If error lines.length is less than 2, how many errors is expecting? How many lines is it expecting to get when we have an error? Should there be more than one line of error output here? that's... I mean, I'm confused. So println runtime. I'm just going to add a second line here of runtime error. And just print that out. So now we have 2. Let's build it and try running this thing. Yeah, now it says unexpected output. I could put it afterwards. No, it still sees an unexpected output, but it's expecting 2 lines. I guess I'd have to go back and look at the code, or I could just run the locks thing here, right? I can just build the Java version of this thing. Where is that? Make test, make C chapters. I can try this and see if this works. And then use their JLocks version to see what's going on. Wow, this is slow. Why aren't these being compiled in parallel? Okay. Do we at least have a Java jar file? There's all the classes. How do I make... Let's make Java chapters. I can just say make JLocks. Why don't I do that? Make JLocks. Okay. There's no jar file. Right. So where's the... How do I run this? This builds a final version of it as it appears. I just want to run it. Okay, I guess this is something I can figure out offline. I don't need to do this on stream. And what I'll do is I'll compare the output of JLocks to the output of locks AST and see what's going on. Obviously adding a second line of runtime error is not the right answer, but it's still, the Dart code is definitely expecting 2 lines. Yeah, it's expecting 2 error lines worth of data. And I only output 1 line. So that's why this is hitting this thing here. Error line 0 has to be expected runtime error. But I don't know what error line of 1 is going to be. Or what is that meant to be? Error lines, let me see what else. Where else do we check? Stack line. Oh, stack. It's a stack output. Stack trace pattern. Oh, wait a minute. I should be putting out a stack trace pattern. It just has to have the same... Huh. Well, I'm confused then because we had to do this to get this to work for some of them. Do we need a different... output format. Because expect runtime error is just going to get this. If I do it this way instead, I'm just going to try this real quick and see if it works. And just put line here on the second line. And if, oops, I don't need that extra one there. Right. Let's see if this works. Wizard says a jar is just zip collection of classes. You don't need a jar to run it. You can run the classes directly. Yeah, that's true, but I was hoping to be able to say Java jar something. So where's the main? There's a statement parser, runtime, return resolver, locks, Java. Well, we'd have to go here, right, and say Java. Sun. No, not Sun. I'm used to working for Sun stuff. S-R, it's Java, crafting, interpreters, locks. Right, yeah, and then it pulls this up. Okay, so I can do it this way. And if I give it the test that we're working with, the test that's failing, which is this guy here. Oh, in that window. Yeah, so undefined variable not defined, and then line 1 is afterwards. Okay, so that's fun. Let me try running this. Oh, I have this all backwards and all wrong. Okay. I'm trying to go too fast is the problem. So I want token line at the end here. Yep. Okay. Let's build that. Make sure the output looks correct. All right, so that's, oh, except I have this error at business. And if I take that out, the other tests are going to fail, right? Right? And what is it complaining about here? Formatting. Oh, because I have token as string. So let's get rid of that. Yeah, so now I have the exact same output, but I think that's going to break the other stuff. Oops. Yeah, so now it's broken this thing, because this is expecting a different output format. Let's run that. Oh, dang it. Yeah, and this is all on one line. So, oh, maybe this is a scanner error versus that's 65, and the not defined one is a 70. Okay, so I think I understand what issue needs to be fixed here. Is we have difference between parsing errors, and maybe there's a resolver error too that we need to do, and each one has its own format. Wonderful. Okay, so that's good to know. And now I'm way over time. So what I'm going to do is maybe tomorrow we can go through chapter 16, right? And then if there's more time, we can keep hacking on this. So I think that's a good use of my time, a good use of my stream. All right, that's that. I am over time. I've gone far too long. Brooke is up and running, doing his U stuff, and so we're gonna go raid him. Let me pause my music and disable that, and I will hopefully see you tomorrow with chapters 16 and a little more error fixing. And meanwhile, we're going to go raid Brooke. All right, have a great day, rest of your day, and I will see you tomorrow. Take care.